Hello, this is Team 1146, and we're participating in the SCUDEM 2024 challenge, working on Problem A, Sweet Tooth and Heavy Metal. My name is Kevin Sony.
I am Macy Mosier.
And I'm Elisabeth Davis.
In the problem we chose, studies have shown that there are heavy metals in chocolate, and we were asked to see how varying consumption patterns of chocolates can affect children. Is rationing the best choice a child can do for their mental cognition and their future, or is eating chocolate all at once not as bad as people make it out to be? And so, in order to begin asking these questions or answering these questions, we used a model developed in the paper, a pharmacokinetic model of lead absorption and calcium competitive dynamics. And in this paper, the authors constructed a model of the human body which measures how the concentration of lead changes and how it interacts with the calcium concentration in this body. And in this model of the body, there are 5 different components that the authors consider: the brain, the blood, the kidneys, the bones, and the other soft tissue. The blood is what interfaces with the other components of the body. It is what transfers the lead and the calcium to the other components of the body. It receives the lead and the calcium from the external environment, and it transmits it to the other parts of the body in a sort of osmosis fashion. And the kidneys is what gets rid of the calcium and lead within the body. So in our model, we make some assumptions, and the assumptions we make are the blood-brain barrier becomes more effective at filtering heavy metals as the child develops. And initially at age 5, there's no lead in the body. And we assume that the individual is healthy and has average characteristics.
Now we're going to begin to develop our differential equation model. And so traditionally, this function n is a sigmoid that represents the chance of a molecule going from compartment X to compartment Y, where lowercase x is the concentration of a molecule in compartment X. And so because calcium and lead compete for the same biological pathways, we're going to replace that small x with the sum of the concentrations of lead and calcium in compartment X. And so now we're going to model the rate of change of a molecule going from compartment X to compartment Y. And so we multiply this n function by the ratio between concentration of lead in compartment X to the sum of lead and calcium, and similarly for calcium. We do the ratio of calcium to the sum of lead and calcium multiplied by this n function. So as lead accumulates in the brain, it becomes less effective at filtering it, so it's modified. So the original transfer function is modified by the z function. And so the only important part of the z function is that it is decreasing with respect to the concentration of lead in the brain. And so as the concentration of lead increases in the brain, blood-brain barrier becomes less effective at filtering out lead. And so originally, this parameter b, which represents the efficiency of the blood-brain barrier, was just a constant, but now we have modified it to become less sensitive as an individual develops. And so another modification from the original model to ours is how we model the intake of lead over time. And so originally the intake of lead was this constant p, and so we've changed this to be a square wave that is non-zero at holidays and birthdays. And then C, which is the environmental intake of calcium, is going to remain constant. And so now we're able to develop a set of differential equations to describe how lead and calcium move between these different compartments. The most important compartment is the brain and the amount of lead that goes in and out of it, and that's what the two terms in the time derivative of the brain lead represents. And an addition we make to the original model is this damage function that is this is going to be the accumulation of damage over time, and at each point in time it's going to be proportional to the concentration of lead in the brain.
Here we run 2 sample simulations with Halloween occurring 26 weeks after the child's birthday, with the blue curve representing the lead level in the brain in micrograms per liter without rationing, and the red curve representing the level with rationing. As you can see, the levels rise up to a maximum of about 0.8 at 150 weeks, or 3 years, and slowly decrease thereafter. This can be attributed to the increasing efficiency of the blood-brain barrier as the child ages. We also note that the blue curve initially goes above the red curve and then meets it again at the next holiday event. This indicates that the effect of lead consumption on levels in the brain is initially linear. The bottom graph shows the estimated effect on cognitive outcomes in units of thousandths of an IQ point. Here the curves remain close together, with the value without rationing slightly exceeding the value with rationing. And here we run a simulation for each value of the date of Halloween as an offset from the child's birthday, from 0 weeks on the left to 50 weeks on the right. As you can see, the curve for the estimated damage without rationing is mostly linear as a function of this offset, meeting the curve for the value with rationing close to the end. The difference never exceeds 13% and can be attributed mainly to the timing of the onset. So given that we assumed a chocolate lead level equal to the highest recorded in the study, our model did not predict any significant effect, whether with rationing or without. The most significant factor is the age at which the child begins consuming chocolate, which affects the total amount consumed. This effect is amplified by the immaturity of the blood-brain barrier at earlier ages. Our model found only a small difference for children whose birthdays are relatively far from Halloween, and this can be attributed to increased overall consumption at earlier ages. Our model also found only a small difference between the case where the chocolate is consumed immediately after the holiday and the case where the chocolate is rationed over a longer period of time, which can again be attributed to onset timing. We used a relatively simple model where the increasing efficiency of the blood-brain barrier was estimated only approximately. We also used a cumulative damage function that's linear in the amount of lead in the brain over time. Although it's known that lead has nonlinear effects on cognitive outcomes, we believe that this is accurate as an approximation for low levels of lead. We also did not model the effects of cadmium or arsenic. This concludes our presentation. Thank you for watching.
Okay.
That should
9
be
minutes.
okay, so